Welcome to the Crazy Hat Chemist. So here we go. Hey, this is the last video in this series of thermochemistry, so that's exciting. So let's get moving. Bam! So today we're talking about the standard heat of formation calculation. We're going to determine the standard heat of formation for the combustion of methane, that's CH4. We're going to use a table of standard heats of formation. Now this table is either within your textbook in this unit or as an appendix. So one or the other, you're going to find some values there, probably in the appendix of your textbook. So the first thing that we're going to do is we're going to get the balanced equation for the combustion of methane. So methane is CH4, just like I've written it for you. So what is necessary for combustion? Combustion, that is a combustion reaction. What is necessary for combustion? So you got CH4 plus O2, that's molecular oxygen because it's diatomic. And what are the products always of a combustion reaction? That is carbon dioxide and water. So now that you know that information, you got the CH4 plus the O2 produces carbon dioxide and water. Now you're going to need to balance the equation. That's essential that you balance it. Okay, so bam. Okay, this is the balanced equation for the combustion of methane. So that's CH4, it's a gas, plus 2 moles of O2, that's a gas. You got that arrow. The delta above the arrow is indicating that this is a reaction that requires something like a spark or a matchlet, something like that, to make it go forward. Then on the product side, you have 1 mole of carbon dioxide gas plus 2 moles of water liquid. Okay? All right, so make sure you pay particular attention to the stoichiometry of this problem and the state of matter of which each reactant and product is in. That's going to be essential. Okay, now we need to know the equation. And here's the equation. This is delta H naught. So see that little superscript 0? That's read as naught. Okay, so that means it's in the standard state. Okay, so delta H naught is equal to the summation, that's the sum of, that's a sigma symbol, the sum of the delta H naught of formation of the products minus the sum of the delta H naught of formation of the reactants. So I don't know if you listen to this radio station or like it or dislike it. It doesn't really matter, but it's NPR. That's NPR. So that's N for naught, P for products, R for reactants. So hopefully you got that. And then that way you don't forget it's products minus reactants. All right, got that good. Okay, then from that data table in your textbook, you will find the following information here. Now, I've had a partial table here because I don't want to have the whole entire table written out. But these are standard heats of formation at 25 degrees Celsius and 1 atmosphere. So when it is delta H naught of formation, that means formation of that compound from its elements in standard conditions, and those standard conditions are 25 degrees Celsius and 1 atmosphere. That's what that little circle, that superscript circle denotes, is 25 degrees Celsius and 1 atmosphere, standard conditions. Okay, so now I've included in this table water that's a liquid, that's negative 285.8. You should look at the units here, and those are kilojoules per mole for all of them. Water that's in the gaseous state, negative 241.8. Hydrogen peroxide, liquid, negative 187.8. Methane, that's a gas, negative 74.86. Carbon dioxide, that's a gas, negative 393.5. Then oxygen, that's a gas. There's no value for that. Okay, it's actually many times not found in your data table or in the appendix. That is, elements in their standard state are not found in the table. Some tables have them, some tables don't. But if it's not found in your table, then how are you supposed to solve this problem? Well, here's the key. And the key is that elements that are in their standard state have a delta H naught of formation that is a value of 0. So what's the value for the oxygen? It is 0. Okay, now what I want you to do is look at that balanced equation that we had before, okay, and then look at the values here of the partial table. Some of these things you're going to use and some of them you're not. For example, you are certainly not going to use the hydrogen peroxide because that's not even in the balanced equation. The other thing that you're not going to use is you're going to look at the state of matter for water that's in the balanced equation, and it is water that's a liquid. So you are not going to use the water in the gaseous state. So you have to use the water in the liquid state because that's what that balanced equation has. Okay? All right. So reference the previous slide for all the values from the table. So it's products minus reactants. The products are the carbon dioxide and the water. The reactants are the methane and the oxygen. You're going to use the stoichiometry of this problem and the values that were on that previous table. So delta H naught of the reaction is equal to 1 mole of carbon dioxide and its value from the table plus 2 moles of water times the value for that table. Remember, it needs to be in the liquid state, minus 1 mole of methane plus times the value that's in the table, plus 2 moles of oxygen times the value that's in the table. So let's plug in the values that are in the table right here. Okay, now those values that are in the table are kilojoules per mole. Make sure you note that. Okay, I included that in the prior step, but I wanted to make sure that the numbers were large enough that you could actually still see them. So you should see that the carbon dioxide is right there at negative 393.5 kilojoules per mole. The water that's in the liquid state is negative 285.8 kilojoules per mole. The methane is negative 74.86 kilojoules per mole. And the oxygen is 0 kilojoules per mole. So you're going to cross out the oxygen part, okay? And then you're going to add up the two products that's on the left-hand side of this. And don't forget about that minus sign, and then the sign in front of the methane is a negative as well. So that's a negative times a negative, you know that's a positive. So here are just the numbers without any units or formulas so that they are larger so that you can see them right there. Okay, now what we're going to do is we're going to do what is necessary following the rules of PEMDAS and your math. That is doing what's inside the parentheses first, then that multiplication, then the addition, okay? And then we're going to get this value. So the delta H naught for the reaction of the combustion of methane, 1 mole of methane, is equal to negative 890.2 kilojoules, okay? Notice that this value is negative, therefore it is exothermic, okay? So, as all combustion reactions will be negative for the delta H naught for the reaction because they are combustion reactions, they produce heat, the temperature increases, if you will. I'm not done with this because I got something else to show you here. Okay, so don't go. Okay, so if you are a scientist, you are well, I'm a scientist right there. I used to work a long time ago at the California Regional Primate Research Center when I had hair and a much larger beard. Okay? If you are a scientist, you are a genius. I mean, it's elemental that you are a genius because you can see that right there. It's elemental. Okay? I am the Crazy Hat Chemist, and you have finally finished all the videos for this thermochemistry series. That means it's time for you to graduate onto the next unit here. Okay, that's why I'm wearing a graduate cylinder on my graduating cap. If you like that video, subscribe to my YouTube channel and give me a thumbs up on that YouTube channel. Find my website online. All my worksheets are on there, and all the videos for all my units are on my website. I'll see you next time. Bye for now.